Mm-hmm. 0, 5, 5, 1. All right, so negative 1 times that makes that 0. Negative 5 and 3 is negative 2. Negative 1 and negative 1 is also negative 2. Now what?
Negative 5 and negative 1 is negative 2.
What now?
There in that bottom right of that right there.
Mm-hmm.
Negative 5 and added to row 3. Negative 5 plus negative 1.
Let's get a 1 here. We have to row reduce this. We need 1s on our pivot, so let's get a 1 because we're going to have to go back up, and then we'll worry about this later because I really don't want fractions right this moment. Okay? So I would divide this by negative 2 or multiply negative 1/2 times row 3. 0, 0, 1, 1. Now in my mind it's going to be easier to go back up. And I'll worry about that 5 again when I get to the end because I really don't want a fraction over here. So now I'm going to multiply negative 5 times row 3 and add it to row 2. Negative 5 and 5 is 0. Negative 5 and 1 I think is a negative 4. While I'm at it, I need to get rid of this one. So I need to multiply negative 1 times row 3 and add it to row 1. So there's a 1, there's a 2. Negative 1 and 1 is 0. Negative 1 and 0 looks like a negative 1. Okay. I need to get rid of the 2, but at this point I would like this to be a 1. I can handle a fraction over here now, so I would get that to be a 1. Multiply 1/5 times row 2. And I know y'all are checking my math because y'all have been checking it the whole time, right? The last step would be, how do I get rid of the 2?
Row 2 minus negative 2 added to row 1.
Negative 2 times row 2 added to row 1. Negative 2 and 2 is 0. That stays a 0. That's 8/5 minus 1 looks like 3/5. Okay, that is what we've been doing this semester, all semester long. They want the solution as a vector. What is the solution? Okay, x1 is 3/5. x2 is negative 4/5. And x3 is 1. To write it as a vector, it's the vector 3/5, negative 4/5, 1. This is the way the solution goes. This is the vector form. Okay, that was number 12. No question about that. Okay, see what next slide shows. All right, this is an important statement. The equation ax equal b has a solution if and only if b can be written as a linear combination of the columns of A. All right, going back just one second to this problem right here. That statement that I just told you was important says that AX equal B, this thing right here, has a solution if and only if B can be written as a linear combination of these columns. That's what these things are. These are the weights that are in your linear combination. So when I solve this whole thing, this told me that if I multiply 3/5 times this first column up here of A, 1, -3, 0, and if I multiply -4/5 times the second column, and if I multiply 1 times the third column, and if I add those all together, I should get 0, 1, -1. Solving that is what this says. I can write B as a linear combination of the columns of A. That's what that says, okay? Do what?
How does it say that 30?
Yeah, y'all are welcome to check it, but I don't want to check it with those fractions. But it'll work out, okay? It will work out. All right, this next theorem is extremely important. If A is an m by n matrix, then the following statements are logically equivalent, which means they are either all true or all false. If one of them's true, if this is true, then the other three are true. If this one's true, those are true. But if that one's false, they're all false. Okay, one of them implies the other. So, for each B and Rm, the equation AX equal B has a solution. That means that B can be written as a linear combination of the columns of A. It means that the columns of A span Rm, that dimension right there. And it means that A has a pivot position in every row. If A has a pivot position, then every B it can be written as a linear combination of A. If it has a pivot position, the columns of A span Rm, not Rn, but Rm. And if that has a solution, the columns span. They're all related. Oh, I don't want to go to that yet. Sorry. All right, I want to look, before I go to this multiplication thing, I want to look at a few other problems, because you have to answer questions based on that theorem. Look at number 14. Let U be this vector and A be that matrix. Is U in the subset of R3 spanned by the columns of A? Why or why not? This is based, how you solve that problem is based on that theorem that I just said is extremely important. How can I tell if that vector U is in a subset of R3 that is spanned by the columns of A? And do what with it? Yes. Augment the matrix, reduce it, and see if it has a solution. Because that theorem says if it has a solution, you have to have a solution. You have to have a solution, sure. Yeah, if you find a solution, then the columns of A are going to span. So if it's in the subset, all we have to do is augment and reduce. Do we need to go through that? Okay. No. So number 14. All right, U is 2, -3, 2, but I'm going to go ahead and write A and augment, okay? So I have 5, 8, 7, 0, 1, -1, 1, 3, 0. That's my matrix A, sorry. And then I'm going to augment it with 2, -3, and 2. Okay, how do I reduce this thing?
One, gotta go.
The one's got to go. So negative, nope. How am I going to get the one to go?
We're gonna get rid of 5 on top first.
All right, well,
Or you could go with,
there's an idea. You could permute it to get the 1 at the top.
you could bring the 0 down, would you think?
Pardon? You
Are you
can.
thinking bringing the 0 down?
No, I was thinking, I think what he was thinking is he would like a 1 right there so you can permute and move that whole row up. You can interchange 1 and 2, 1 and 3. So I'm liking that because I'd like the 1 at the top. Because all these can't be divided by 5, so if I go ahead and divide this by 5, I'm getting a bunch of fractions already, and that looks ugly. So 1, 3, 0, 2. I could leave 0, 1, negative 3 here, and I have 5, 8, 7, 2. Now it's easier. Now to get rid of the 5, I can multiply negative 5 times row 1 and add it to row 3. 1, 3, 0, 2. 0, 1, negative 3. Negative 5 and 5 is 0. Negative 15 and 8. Negative 7. Positive 7. Negative 10 and 2. Negative 8. All right, then it looks like I need to get rid of this negative 7. So I would just go ahead and multiply 7 times row 1 and add it to row 2 and add it to row 3. Zero, 1, negative 1, negative 3, 0. 7 minus 7 is 0. Negative 7 and 7 is also 0. Negative 21 and 8, negative 21 and negative 8 is negative 29. Did I make a math mistake? Anybody? Okay.
0 came from
All right, so 0 cannot equal to negative 29. So how does this help us answer the question? Once you get to this point, if you don't answer the question, you've done nothing. The question is U, this vector right here, in the subset that is spanned by these 3 vectors? No, because there is no solution. No. U is not in that subset. All right, so you have to go through the process and then answer the question. Okay. We okay there? So number 15. Same kind of question, except your matrix A is 2, negative 1, negative 6, 3. Your B equation is a B sub 1 and a B sub 2. And this one says, show that the equation AX equal B does not have a solution for all possible B's. And then describe the set of all B for which AX equal B does have a solution. So I've got to show that it does not have a solution. To show that it does not have a solution, I need to augment and reduce this thing. So augment 2, negative 1, B1. There's a B2. Negative 6 and a 3. So augment, and let's reduce it and see what happens. So I need to get rid of the negative 6, so I would multiply 3 times row 1 and add it to row 2. So this stays the same. Negative 6 minus 6 is 0. Negative 3 and 3 is 0. 3 times b1 plus b sub 2. Sorry, my plus b sub 2 is hanging outside my matrix. Sorry about that. All right, how does this show that there's no solution? How does this show that it doesn't have a solution? 0 cannot equal to 3b plus b2 for some b1s and some b2s, right? Not for all of them, but for some of them. All right, part B of this, or the second question was, describe the set of all b's for which ax equal b does have a solution. When will it have a solution? Has a solution when what? Go back up here. When will this have a solution? When this is 0. When this thing right here is 0, then you've got a whole line of zeros and you will have a solution. In fact, you'll have an infinite number because you'll have a free variable. It'll have a solution when 3b1 plus b2 equals 0. That's when it has a solution. So whatever it takes for b1 and b2 to be 0, to make this whole thing 0, that's when it'll have a solution. Question? Okay, everything we've talked about is related. We're talking about the same things we talked about in section 1.2, but we're just using different words. You're going to find that a lot, okay? All right. I'm going to answer some of these questions. In number 17, they give us a matrix A, and it says how many rows of A contain a pivot position, and does the equation AX equal B have a solution for each B that's in R4? All right, here is matrix A. 1, 3, 0, 3. Negative 1, negative 1, negative 1, 1. 0, 4, negative 4, sorry. 2, negative 8. 2, 0, 3, negative 1. Here is matrix A. I think I copied it wrong. And this is negative. How many rows of A have a pivot position? It's a simple question. How do we find out? Can you look at it and tell? You'll have to reduce it. You'll have to reduce it. All right, I'm going to give y'all a minute actually to reduce this. And I'm going to put this thing on pause, which means it's probably going to have to pick up and do 2 separate recordings.